All right, rock and roll. Hello, everyone, and welcome to our presentation on weather patterns and severe storms. Let's go ahead and get started. Boom. When we're talking about weather, we're going to be talking about air masses, and we are on slide 3 of the presentation here. To read the textbook definition, an air mass is an immense body of air. That means a very large body of air that is characterized by similar temperatures and amounts of moisture. So it's a big area of air that's about the same temperature and the same humidity. Now these air masses, they can move around. And as it moves, the characteristics of an air mass change. So does the weather in an area over which the air mass moves. So as these different masses move around, warm air, cool air, humid air, dry air, as they move around, they change and they affect the weather down here on the ground. So now we're going to look at some of the ways that these moving air masses affect the weather for those of us who live down on the ground. All right, on slide 4 we see an amazing picture of some tornado damage. You can see the way these air masses move and interact. Sometimes we can get winds so strong that it'll drive a piece of metal into a wooden pole. We are going to talk about tornadoes later in the presentation. So we may come back to this picture in a little bit. But for now, let's move on. Here we see an example of one of these air masses moving. In this example, we have a blue circle at the top of the page. And that blue circle represents cold, dry air. And in this example, that cold, dry air is moving south from Canada to the United States and down to Mexico. Now you can notice that as it moves south, that cold air gets warmer and warmer. You can see the temperatures of that air mass at 7 or 8 different points along its trip. Notice as it moves south, that cold air gets warmer and warmer. All right, here we go. Air. Let's talk about how we classify these air masses. On slide 6, we see a definition. In addition to their overall temperature, air masses are classified according to the surface over which they form. And we're going to see that on slide 7. Here we have 4 different types of air masses here. Let's start with the top of the page. Notice that those 4 blue air masses all have the letter P in their name. We have MP and CP. Now that large P stands for polar. P-O-L-A-R. Polar. Polar simply means in high latitudes, far from the equator, close to the poles. So close to the North Pole or close to the South Pole, but far from the equator. Places where the air is very cold. So that P, cold air very far from the equator. Notice the three red circles at the bottom of the page all have the letter T, the capital letter T in their name. That T stands for tropical, which just means close to the equator. And you know, the air close to the equator will receive more direct sunlight, so it's going to be warmer. So we have the cold air close to the poles and the warm air close to the equator. Notice there are two other letters in these names that we need to worry about. We have M and C. Now, M stands for maritime, which just means the sea. So maritime air is going to originate over the sea, over the ocean. The C stands for continental. Continental means over land or over a continent. So maritime air comes from the sea. Continental air comes from over land. So with these four letters, we can make combinations to describe four main types of air masses. Let's start in the upper left-hand corner right here. Notice we have maritime polar. Remember, maritime means over the sea, over the ocean. Polar means near the poles, far from the equator, where it's very cold. So maritime polar is going to be cold air over the ocean. Let's move here to the right. We see continental polar. Continental over land, polar near the poles where it's cold. So continental polar will be cold air over land. Like maritime polar, it's going to be very cold, but it's also going to be very dry. Let's move down here to the lower left. We see maritime tropical, MT. Maritime tropical, maritime means over the sea, tropical close to the equator where it's warm. So as you might expect, that's going to be warm, moist air. It's going to be warm and wet. The next one here, in the bottom half of the page, in the middle, we see continental tropical, as you might expect, continental over land, tropical in the tropics near the equator. That's going to be warm, dry air. So we're going to have cold, wet air, cold, dry air, continental polar, warm, wet air, maritime tropical, and warm, dry air, continental tropical. All right? Let's move on. Slide 8, we see that much of the weather in North America, especially weather east of the Rocky Mountains, is influenced by continental polar and maritime tropical. Let's go back and look at that map one more time and see what they're talking about. East of the United States, that means this area right here. Influenced by continental polar, that would be this air here. Remember, the cold, dry air. And the maritime tropical down here. Remember, the warm, moist air. The warm, wet, humid air. So that's those are going to be the two main forces that affect the weather in the eastern part of the United States. That cold, dry air coming down from Canada and the warm, wet air coming up from the Gulf of Mexico. Here we go. On slide 9, you can see a little bit more detailed description. Continental polar air mass, uniformly cold and dry in the winter, cool and dry in the summer. But notice they're always going to be cool and dry. Then the maritime tropical. Remember, that's from the sea, from near the equator. So it's going to be warm and wet. Maritime tropical air masses are warm, loaded with moisture, that means very wet, and usually unstable. That means they change very easily. They do not stay the same. Maritime tropical air is the source of much, if not most, of the precipitation received in the eastern two-thirds of the United States. That means it is the source of our rain. So our rain comes from maritime tropical air. It is the source of the precipitation. The rain comes from maritime tropical air. All right? Maritime pole. All right. So where does that continental polar air come from? Well, actually, a lot of this air, this starts out as maritime polar. And we're going to see how that happens. Let's look on slide 10. Maritime polar air masses begin as CP in air masses in Siberia. Remember, Siberia, that is the eastern part of Russia. So we have continental polar. That's going to be cold, dry air. Air that's over land in a polar area, cold and dry. So the cold, dry, continental polar air changes into relatively mild, humid, unstable maritime polar air during its long journey across the Pacific. Now there's a picture of this on slide 11. Here you can see that cold, dry air moving southeast from Siberia. And as it moves, it becomes a little bit warmer, so it goes from cold to cool, and it becomes more moist. So we start up here with cold, dry air, and we go to cool, moist air. Here, let's move on. Slide 12, continental tropical air masses. Remember, these were the air masses that start over land in the tropics. So it's going to be warm and dry. Only occasionally do continental tropical air masses affect the weather outside of their source regions. So they do not affect the weather very far away. However, when a continental tropical air mass moves from its source region in the summer, it can cause extremely hot, drought-like conditions in the Great Plains. Movements of continental tropical air masses in the fall often result in mild weather in the Great Lakes region, often called Indian summer. Let's go back to the map to take a look at that. We're going to go back to slide 7. Notice the continental tropical air masses in the United States, at least, start down here, over land in a very tropical warm area. So it's hot, dry air. Now they don't often affect the weather outside of their source regions. So they do not move very much. They kind of stay home. That hot, dry air usually stays down here and does not move. But sometimes it does move up to the north, and it brings very dry, hot weather. Remember on the last slide it said they bring drought. A drought means a period of very dry weather with no rain. This is often very bad for farmers who need that rain to grow crops. But when that hot, dry air comes up, it does not rain, and very often we see a lot of crops being destroyed. Many crops die. Sometimes in the fall, in October and November, that air will come all the way up into the Great Lakes region. That means this part of the United States and Canada. If that warm air comes all the way up here, this area of the country will have very warm weather, even in October. So we call this an Indian summer. That really just means it's a very strange summer. It's like a second summer. The weather that is very hot in the summer, then in September and October it will get cool and cold, but then when that continental air comes up, it will get warm again in November, maybe just for a couple of weeks. For a short time, it will get warm again. So we call it an Indian summer. All right? Let's move on. I think we are on slide 13. All right. All right. So we've talked about these four different types of air masses: the continental polar, the maritime polar, the continental tropical, and the maritime tropical. And we understand what those mean in terms of where they originate. Remember, maritime polar, over the ocean, near the poles. Continental polar, over land, near the pole. Maritime tropical, over the ocean, near the equator. Continental tropical, over land, near the equator. All right? But what happens when they meet? What happens when one air mass, like a continental polar, meets an area of, say, maritime tropical? Well, the place where they meet we call a front. The definition is there on slide 13. When two air masses meet, they form a front, which is a boundary that separates two air masses. Okay. I want to point out this word front. It's also the word we use in war when two armies meet. When one army controls this area, another army controls this area, the place where they meet is called the front. And we use the same word for the armies and the air masses. So you can kind of think of it, these air masses, like two different armies, like an army of warm air and an army of cold air meeting together. And we're going to look at some different things that can happen. All right, we'll start with our two basic type of fronts. First, a warm front. A warm front forms when warm air moves into an area covered by cooler air. So if we have our warm front army and our warm air army, our cold air army, when the warm air starts to win, we call that a warm front. If the cold air starts to win and the cold air pushes the warm air, it's called a cold front. So we get warm air pushing the cold air, warm front, cold air pushing the warm air, that's a cold front. Now that happens in different ways. We're going to take a look at that in the illustrations on page 15 and 16. Here. A warm front, you can see, remember, that warm air pushing the cold air. Now remember, warm air. With warm air, the air molecules are going to have more energy. So they're going to move faster. So they're going to be farther apart. So warm air is going to be lighter than cold air. This is an important thing to remember when we look at warm fronts and cold fronts. The warm air is light and cold air is heavy. So when that warm air pushes that cold air, the warm air will actually move up and over the cold air because it's lighter. Right. So you can see look in the illustration on page 15 that light warm air is rising and pushing the cold air. As a warm front comes toward us, we can see a warm front coming because of the different types of clouds. And this is a really excellent picture because it shows you the 4 basic types of clouds that come with a warm front. Notice at the very beginning of the warm front, we see the cirrus clouds. That's in the upper right-hand picture, the upper right-hand corner of the picture right here, the cirrus clouds, right along this line. That would be the edge of the front edge of that warm front, the very beginning of the warm front. Those cirrus clouds, they're very high. They're around 5,000 meters. And they're very thin and very wispy. An interesting fact, the word cirrus actually comes from a Latin word for like a curl of hair. So the Romans gave those clouds the name cirrus because they looked like hair. So very thin, wispy, almost like hair. Cirrus clouds. Now, as those cirrus clouds grow, they get thicker and heavier, and they become the next type, cirrostratus. That's when the cirrus clouds start to grow together. More warm air is coming up, and actually goes from water vapor, it freezes. We go from vapor to ice without ever having liquid water. So from cirrus, the cirrus clouds grow together into cirrostratus, and then as the warm front moves along, those cirrostratus clouds become almost like big blobs, little blobs of clouds that are heavier, they're lower. Notice now we're down around 4,000 meters, and those are the altostratus. As the clouds get bigger and thicker and heavier, we end up with nimbostratus, which bring light precipitation, light rains. So a warm front is usually going to bring light rain, a little bit of rain, followed by warm air, warm sunny weather. So now that when you know this, you can actually see these fronts coming because you can see the cirrus clouds followed by the cirrostratus, then the altostratus, nimbostratus, a little bit of rain, and then warm sunny weather. That's how a warm front passes. Now, let's talk about cold fronts. When the cold air starts to push the warm air out of the way, it's a little bit different. Because remember, the cold air is very dense and it's heavy. So the cold air, when the cold air pushes the warm air, it actually moves under the warm air. Remember on slide 15 that warm air pushes the cold air and goes up. The cold air pushes the warm air, but it stays down. So it's almost like a wall of cold air. So that warm air, which you can see here on the right, here we've got the warm air on the right, the cold air on the left. As the cold air moves from left to right, the warm air is pushed up very quickly. So all that warm, wet air, with a warm air with a lot of humidity, is pushed up very quickly. So it condenses very, very quickly. So we don't get that slow progress from cirrus to cirrostratus, altostratus, nimbostratus. We get this very quickly accumulation into cumulus and cumulonimbus clouds. So cold fronts tend to bring very heavy precipitation, very heavy rain, and thunderstorms. One thing I forgot to mention that I want you to take a look at. Notice the symbols that we use. For that warm front, right here, we use the red half circles. And those circles point the direction the front is moving. And here, the same thing goes with the cold front. We've got the cold air behind that line. They point in the direction the front is moving. Two more types of fronts, which are a little bit more complicated. Stationary front. Occasionally, the flow of air on either side of a front is neither towards the cold air nor towards the warm air, but parallel to the line. To show you what that would look like, very briefly, let's say we have, remember, so with a warm front, our warm air is pushing the cold air. With a cold front, our cold air is pushing the warm air. With a stationary front, we have two air masses, warm and cold, but they're moving more like this. They're not pushing each other. They're just moving against each other. Almost like two lines of traffic on a road. You know, when you're driving down the road, the air, you might have traffic on the left side moving north and traffic on the right side moving south. They're not pushing each other. They're just moving against one another like this. And the other type is an occluded front. That's when a cold front overtakes a warm front. When we have a warm front, so here we go. I'm going to get another piece of paper here to illustrate this for you. Remember, with our warm front, we've got the warm air pushing the cold air, but sometimes another mass of cold air comes behind it and actually overtakes the cold air. So two areas of cold air actually meet and push that warm air up together. That's an occluded front. We're going to take a closer look at both of these right now. Here we see a here is an occluded front. You can see that in the middle is that warm air, and it's pushing the cold air on the right. So we have a warm front moving from left to right, and you can see there on the front boundary, on the very far right, we have our cirrus clouds, our cirrus stratus, our altus stratus, and our nimbostratus here, and the light precipitation from the nimbostratus, like we learned with warm fronts. But over on the left side of the picture, we have a cold front. And that cold front is actually moving faster. Just like, picture two cars on a highway moving the same direction. One car is moving faster than the other, so it eventually catches up and passes that car. The same thing's happening here with that cold front on the left eventually catches the warm front. So the cool air and the cold air meet, and together they push the warm air up, and we get so that warm, moist air rises very quickly, it cools very quickly, condenses very quickly, so we get a lot of rain very quickly. When this happens, we usually get a very quick downpour, and then the rain disappears quickly. We might have a thunderstorm moves in, heavy downpour, and then the rain is gone. I think you've probably all experienced this before. This happens quite often in Thailand. We have a storm front will move in, we'll get very heavy rain, and then the rain will be gone in an hour. This happens almost every day during the rainy season here in Thailand. This is an occluded front. Now we're going to talk a little bit more about stationary fronts in a little bit, but stationary fronts, remember, the two air masses moving in opposite directions, like cars on a highway. They tend to form cyclones, mid-level cyclones. Now these mid-latitude cyclones are large centers of low pressure that generally travel from west to east and cause stormy weather. Like I said, they form with stationary fronts, and we're going to take a look at that on the next slide. Well, first we're going to have a picture. Here you can see a cyclone forming over the United States. A massive storm turning in like this. Now you can notice a couple of things about this picture. You can actually see several different types of clouds. Here on the outside of the storm, we see cirrus clouds. The very thin clouds, remember, cirrus, like hair. And here, the very thick cumulus and cumulonimbus clouds. So we've got the thick cumulonimbus and the light, thin cirrus. Here's the illustration I was talking about. You're going to see how this happens. Now the pictures are kind of small, but if you look very carefully, you can see what's going on. Let's start in the upper left. So this air mass right here in the northwestern United States near the border with Canada. this is an illustration. Right here we see an illustration of that air. This is a stationary front. Notice we have the warm air moving to the right and the cold air moving to the left. So the air masses, the warm air and the cold air, they're not pushing each other. They're just moving like this against one another. But what happens in step 2? You can see over time we start to form this U shape. The cold air starts to bend in. The warm air kind of bulges and starts to push on that cold air, especially up at the top. Then when that happens, we end up with cold air pushing in one way, warm air pushing in the other. So they're both moving in the same direction. Here, both are moving counterclockwise, but they're all that we get a warm front and a cold front, that are almost like two hands on a clock, but of course moving counterclockwise. But they're like two arms swinging in the same direction, rotating in the same direction. So we get warm air moving like this, cold air moving in behind it. So what ends up happening, the warm air is moving counterclockwise, the cold air is moving counterclockwise, all of the air on both sides gets pulled in, and we end up down here with a cyclone. You can see the warm air being pulled in this way, the cold air being pulled in like this. So the warm air will be pulled in from on the warm side of the front. The warm air will rise, it will become cold, it'll collapse again, and we keep getting this same cycle, and that's a cyclone. The next thing we're going to talk about, airflow aloft. More often than not, air high up in the atmosphere fuels a mid-latitude cyclone. Movements of high air in the atmosphere. Here you can see how that happens. On the down here around the L, you can see we see a low pressure system with that. Remember, like as we talked about, that warm air moving in, the cold air moving in behind it. That warm air is going to rise, and we call that a cyclonic flow. The warm air rises up and sort of turning, rotating as it rises. Over on the left, we see the opposite happening, where that very high air is actually falling in the same type of pattern, and that's when we get what's called a high pressure system, so an anticyclonic flow. Next, thunderstorms. We talked a little bit about thunderstorms when we looked at cold fronts. A thunderstorm is a storm that generates lightning and thunder. They bring heavy winds, heavy rain, and hail. Hail is like frozen rain. It's small pieces of ice falling from the clouds. Next slide, 25. At any given time, there are an estimated 2,000 thunderstorms in progress on Earth. So as we speak, there are small thunderstorms all over the planet. The greatest number occur in the tropics, where warmth, moisture, and instability are common atmospheric conditions. So where you have a lot of warm, wet air that's very unstable, that changes a lot, that's where you're going to find thunderstorms. They form when warm, humid air rises in an unstable environment. Here we see an example. here on the left, that warm, humid air rising up very quickly. It rises up above 5 kilometers, above 5,000 meters. Remember when we talked about warm fronts, we said the cirrus clouds at the beginning of the warm front form around 5,000 meters. So when you look at a thunderstorm, you're looking at a lot of hot air rising up much higher than the edge of those warm fronts. As that warm air continues to rise, we may get cool air fall. The warm air is going to rise up, it's going to cool, it's going to fall back down, and that's when we're going to see very heavy rain. And then you can see later what we call the dissipating stage. That warm air's risen up even farther, and it's formed that flat top. It reaches a point in the atmosphere, it just cannot rise any further. The air is too cold to rise any farther. And so it just rises up. It's like hitting a wall. So it forms what we call the anvil. That the warm air is rising up, all that moisture is condensing and freezing into a cloud, and then it can go no farther. So it just forms that anvil, and will sort of spread out and form that flat top, called an anvil. In this case, around 15 kilometers. That anvil, it tends to be much higher in the near the equator. It can be around 20 kilometers, around 20 kilometers. In the north, or in the far north or far south, far from the equator, that's going to be much lower, maybe 12 or 10 kilometers. All right, let's move on. Tornadoes. Violent windstorms that take the form of a rotation column. To rotate means to move in a circle. To rotate. A column means something that stands straight up. So a rotating column would be something that's moving in a circle straight up and down. We call that a vortex. The vortex extends downward from a cumulonimbus cloud. We often see them with thunderstorms. Let's look at a picture of how that happens. We start up here in the upper left with a mass of air that's spinning along a horizontal axis. Notice that happens when we have very strong winds up high and very weak winds down near the ground. To give you an example, to kind of illustrate this, let's say my hand, I want something flat. Oh, no, I'll be all right. Okay. Now let's say I'm going to push this cup. Now, if I push that cup with the same strength on the top and the bottom, it will move like this. But if I put all my strength on the top, it's actually going to roll. That's the same thing that's happening in that picture in the upper left. The strong winds are on the top, so it's pushing it almost just like this cup that's rolling, that rolls along the surface of my hand. That air kind of rolls along the surface of the earth with the strong winds pushing it on the top, and the air rolls along the earth like a ball or like a log. Now, if that rolling air hits an area that's very warm and it gets hot very quickly, remember that hot air is going to rise up very quickly. So we get what's called an updraft. And we see that in picture 2. So we get that rolling. So the first step, we've got rolling air. Then the second step, the warm air rises up very quickly and sort of pushes that rolling air. And eventually we end up with what we see in 3. We went from air that was rolling, the air was pushed, and now it's spinning up like a vortex. Imagine like a log rolling along the ground, and then it hits a rock or something, and something pushes it up. So it goes from rolling along the ground to bump, spinning up and down like this. That's what happens with a mesocyclone. And you can see the tornado forming at the bottom. Tornado winds, it's too strong for us to get into a tornado to measure the winds directly. So we figure out the strength by the damage that they do. And the scale we use is called the Fujita scale. Like we use the Richter scale for earthquakes, the Fujita scale is used to measure tornado intensity. Tornado watches alert people to the possibility of tornadoes. Tornado warning is issued when a tornado has been sighted or is indicated by weather radar. Here on slide 30, you can see a table of the Fujita intensity scale. Here on the left side, we see the intensity, F0 to F5. Each one of these ratings corresponds to a certain wind speed. So any wind less than 116 kilometers an hour will get an F0 rating. And as you can see, that will be light damage, some branches broken off trees, but very small stuff. That goes all the way up to F5. That's wind that's stronger than 419 kilometers an hour. And as you see there, houses may be lifted off their foundations. Automobiles can be thrown by the wind in excess of 100 meters. Bark is torn from the trees. Yeah, the picture, remember the picture that we saw at the very beginning with the metal stake driven right through the telephone pole? That would be a very high intensity tornado. Hurricanes are another type of severe storm. These are whirling tropical cyclones that produce winds of at least 119 kilometers per hour. In the United States, we call them hurricanes. In the Indian Ocean, they are called cyclones. In the Indian Ocean, they are called typhoons. In the Pacific, let me switch that. In the Atlantic, they are called hurricanes. In the Pacific, they are called typhoons. In the Indian Ocean, they are called cyclones. All right, so Atlantic, hurricanes, Pacific, typhoons, Indian Ocean, cyclones. Most hurricanes form between 5 and 20 degrees north and south latitude. The northern Pacific has the greatest number of storms, averaging 20 per year. Yeah, this is very true. I know when I lived in Japan, we had several typhoons every year, in especially August and September, toward the end of summer. Bring a lot of. Here's an example. This is a hurricane. Remember, Atlantic Ocean hurricanes. This is Hurricane Floyd, which hit the United States just a few years ago. This actually hit my home state of North Carolina right up here. I remember Hurricane Floyd came up and hit our coast very badly. Did a lot of damage. All right. Hurricanes develop most often late in the summer, August, September, when water temperatures are warm enough to provide the necessary heat and moisture. So the ocean has been getting warmer and warmer all summer long, and finally there's enough heat and moisture in the air to form a hurricane. Notice that picture. We have that little dark dot in the center of the hurricane. So all around us, hundreds of kilometers, we've got heavy rain and very thick clouds, very heavy wind, very strong wind. All of that is moving around this little dot in the center, the eye. Now in the eye, there is no rain and no wind. The eye is a zone of scattered clouds and calm, averaging about 20 kilometers in diameter at the center of a hurricane. I have actually been in a hurricane when the eye moved over us. When I was very young, a hurricane hit my home state, and that eye actually moved right over my house. So we went from it's really amazing to see, because 1 minute there's strong, powerful wind and really heavy rain, and then everything ends in an instant. And there's just some clouds, you can see the sun, there's no wind, there's no rain, and it lasts for a few minutes, and then the storm comes back. But all the wind is moving in the other direction. The eye wall is a donut-shaped area of intense cumulonimbus development and very strong winds that surrounds the eye of a hurricane. Here, when we look at a hurricane on slide 34, you can start to understand why there's no rain and very little wind in the eye of the hurricane. You can see all of that air moving around the eye in these bands of heavy, heavy wind and heavy clouds. As it moves around, that warm air rises, so that we have all that surface here, down here, that surface convergence. The warm air down on the sea is all pulled into the hurricane, and it rises up just like we saw with the mesocyclones. As it rises, it cools. So by the time it gets to the top, the air is much cooler. So some of that cool air flows out, which we call outflow, and some of it falls back down into the center, creating the eye. So here, in this area around the eye, we would get very, very low pressure. And then in the eye itself, very high pressure. The intensity of a hurricane is described using the Safer-Simpson scale. Very much like a tornado, we describe them as Category 1, Category 2, 3, 4, or Category 5, which are the strongest hurricanes. A storm surge is the abnormal rise of the sea along the shore as a result of the winds. That's when we tend to get very high, very large waves along with the storm. And here you can see that Safer-Simpson hurricane scale on slide 36. Notice Category 1 are the weakest hurricanes, Category 5 are the strongest. Alright, so that about does it for our lesson on weather patterns and severe storms. Thank you all very much for tuning in, and I will see you on our next lesson.
like 10 minutes.
10 minutes?